Hi everyone. Today we're going to learn about Zwitterion. So Zwitterion is a very important concept in terms of amino acid. So if you do not know what is an amino acid, I suggest you to go back to my first video, structure of amino acid, and you can come back to this video so that the concept will be more clear to you. So when we talk about a zwitterion is actually a molecule which contains both positive and negative charge. And this is the reason why the zwitterion contains a net charge of 0. So I'll be showing you how does a zwitterion look like. So we all know that the structure of amino acid consists of an alpha carbon, and we have a carboxylic group, right? And then we have an amino group, we have a hydrogen, and then we have an R group. So the R group is responsible for determining or is responsible for classification of the amino acid. So every other thing will be same in the amino acid except for this backbone, right? So this is going to remain the same, and then this R will be different. So I'll be not talking about these things because we already discussed in the previous video. I'll be talking about the zwitterions. So what will happen now is there are two possibilities, So the possibility one is that either this COOH could donate its hydrogen and gain a negative charge, or the other possibility is that this NH2 could gain a hydrogen and then gain a positive charge, right? So this has donated one H ion, and then this has accepted one H ion, right? H plus ion. So as you can see that one end of the amino acid has a positive charge and the other end has a negative charge. So can we say that this is a zwitterion? Yes, of course, this is a zwitterion because it has both positive and negative charge, which has resulted in the charge, net charge 0, right? So now let us see the concept of acid and base, because this is also very important. So when we talk about a pH, we all know that we have pH level from 1 to 14, and in the 7 we have a neutral pH, right? And then when we move to below 7, the pH will be acidic. And if we move upwards, in the upwards direction, the pH will be basic, right? Now in terms of acids and bases, one of the most common thing is that if it is an acid, if a molecule is an acid, it will donate H plus, right? It will donate its H plus. And then if I talk about an acidic condition, right? If I talk about an acidic condition, that means the H plus ions will be more when the solution is acidic. So I can say that if the solution is acidic in nature, there will be more H plus ions, right? Yes, of course, I can say that, right? Now when I talk about a base will accept H plus. And then if I talk about a basic solution, right? If I talk about a basic solution, then it will be very less in H plus ions, right? We all know that basic solution will have more hydroxyl groups, and then acidic solution will have less hydroxyl groups. So this is just a basic concept, but then just like I'm trying to like join the dots so that you can understand. So why are we actually trying to understand the base and acid and all these stuffs is because when we talk about amino acid, this part, right, this is acidic. This is an acid, right, because COOH is an acid. And then if I talk about this, an amino group, this is actually a base, right? So let me just highlight it so that you could be more clear. This is an acid and this is a base. Now let us see how does a Zwitterion is formed. So I've just drawn a basic amino acid. So let's take an example of this one. So suppose if I say that this is in low pH, right? And if I say this as high pH, so now as I told you that when we are when we're talking about low pH, the hydrogen ion is more in terms of low pH, right? So when hydrogen ion is more in terms of low pH, this NH3 has gained an extra hydrogen, right? Before, what was the thing? Before actually, before this was NH2, right? This was NH2. But then, because of the extra hydrogen or the excess amount of hydrogen, it has gained an extra hydrogen. So now it is NH3. Now it has gained a positive charge, right? So it has gained a positive charge. This one will not have any charge because it's like fulfilled on its own. It has fulfilled its valency. So this has a positive charge. So when an amino acid is present in low pH, right, then the charge is usually, what is the charge? It is +1, right? +1. I'll use another color. This is very dull. Okay. So now let us talk about high pH. So when we talk about high pH, wait a minute. Let us not talk about the high pH first. We'll talk about the middle one, right? Where the Zwitterion is formed. So now what will happen is, as the pH is getting raised, because this is low pH and now the pH is getting raised in this particular direction, right? So this is getting raised. Now what will happen is, when the pH is getting raised, hydrogen ions will be little bit less, right? Hydrogen ion will be little less. So now what will happen is, this COOH will be the first one to donate it H plus ion. Why? Because, I'm writing an H. Because as I told you that the hydrogen ion is less, like the hydrogen ion is decreasing in number. Therefore, the COOH is the first one to donate its hydrogen so that, the hydrogen ion can be like maintained in the solution, right? But then NH3 is not donating any charge. Any hydrogen. So the NH3 will be positive because it has not donated its hydrogen. The first one to donate its hydrogen is first to donate. So who is the first one to donate? It is the COOH. Now as you can see, again what is happening? The pH is increasing, right? Now what will happen? The COOH has already given its hydrogen and then it has already gained a negative charge. Now what will happen is, the NH3, let me just write NH3 so that you don't get confused. So I'll just write NH3, and then it had a positive charge, right? Positive charge. Now what will happen is, as the concentration of pH is increasing, the hydrogen ion is decreasing, right? Hydrogen ion is decreasing. Therefore, the first one to donate its H plus was this COO minus. Now, second time, who will be the donator? This will be the donator. So, the second donator will be, second donor will be NH3. So, can I say that the NH3 positive charge will be removed and it will have only NH2 now, right? Because we all know that nitrogen valency is fulfilled if it is making 3 bonds, right? So if you're getting confused about how is this happening, you should go and learn the valency and all these stuff, carbon, nitrogen, carboxylic acid, all these, you should be knowing the valency of each and every atoms. Then only you'll be able to understand this. But then if you're able to understand this, well and good. So let me just repeat what I said just now. So at first, hydrogen ions were very much in the solution. Therefore, COOH already had a hydrogen ion, and then NH3 also took one extra hydrogen, so it gained one hydrogen ion, right? So it had a positive charge. And then now, as the charge is as the pH is increasing, what is happening is the hydrogen ions is getting less in the solution. Therefore, the first one to donate its hydrogen ion to maintain the pH is COOH. Then it will have a minus charge, right? This is there. NH3 is already there. It is not losing its hydrogen. Again, the pH is increasing. Now what will happen is, this had already given its hydrogen previously. Now this will also give its hydrogen and then lose its positive charge. So now it doesn't have any charge. Now if I talk about the charges, right, I'll just remove this so that, because this looks very, just remove it. Yeah. So when we talk about charge, now if I say about charge, what will be the charge of this particular molecule? It has a positive end and then it has a negative end. So the charge will be 0, right? So the net charge will be 0. Now what about this one? What about this one? This will have -1, right? So this is actually the ion that I'm talking about, the Zwitterion that I'm talking about. This is actually the Zwitterion. The Zwitterion, or it is also known as amphoteric ion, because it has one end positive and other end negative. So it is carrying both the charges. So amphoteric in nature as well. So this is actually a Zwitterion, right? So now, let us try to understand more. So I wanted to talk about pK value, and then pK, what exactly is a pK value? So pK value is actually the acid dissociation constant. How quickly does, any molecule loses or donates hydrogen? So that is what we are going to study now. So when we talk about pK1 and pK2, the most common thing that you need to remember is that pK1 is associated with the carboxylic group, right? And then pK2 is associated with the amino group. So if I'll be very simple with what I'm trying to say is, when COOH loses its hydrogen or donates its hydrogen, that value is the pK1, right? When this should be actually NH3 because then it will be losing the hydrogen, right? So when NH3 will lose one hydrogen, right, that will be termed as pK2. I hope you're able to understand. I hope you're able to catch what I'm trying to say. So now let's talk about the isoelectric point and what exactly are these pK1 and pK2 value. So why is it important? Why do we need to know the pK1 value, pK2 value? So now let us see that. So we talk about the isoelectric point now. Okay, so what is an isoelectric point? So an isoelectric point is actually a point, or it is also known as the pH, right? It is the pH at which a particular molecule carries no net electric charge. So can I say that the zwitterion that I was talking about, can I say that this zwitterion that we just made, this is actually the isoelectric point of this amino acid because it is carrying a zero charge, a net charge of 0, right? So now let us see how does an isoelectric point mean and how do we calculate an isoelectric point. So when we talk about glycine, yes, so I just think I'll just take this one. Okay, so in glycine, as you can see that the pKa value is pK1 value, sorry, pK1 value is 2.34 and then the pK2 value is 9.6. So if I want to calculate the pi, if I want to calculate what is the isoelectric point, right, isoelectric point for this particular glycine, so I know that the pK1 value is actually the pH at which the COOH will lose its hydrogen, right? And then pK2 value is actually the value where NH2 will lose its hydrogen, right? So I'll just try to make you understand what exactly I'm trying to say. So when So when 2.34, right? So this particular amino acid is actually, it is below, it has not reached 2.34, right? So when this particular amino acid reaches 2.34, that means if it reaches this point, right, this point, then what will happen is that this particular amino acids COOH will lose its hydrogen, and then since it has an extra hydrogen, it has a positive charge, right? So this is the first value where COOH loses its hydrogen. So now when we talk about the other one, now where is it? 9.36, yes. So when this amino acid reaches 9.6 pH, what will happen is this had already lost its hydrogen, right? Now this was actually before this was NH3 plus. Now this NH3 plus will also lose its hydrogen, right? So it lost its hydrogen and it has become NH2. So now as you can see that this is actually the zwitterion, right? So this is the zwitterion. And then this has a charge of +1. This has no net charge. It has a charge of 0, and then this one has -1, right? So now if you want to see the isoelectric point, where, you know, we want to see this particular point where the charge of the amino acid has become 0. So now when we see that, let us just apply the formula. So when we talk about isoelectric point, we just add the pK1 value and then pK2 value, and then we'll divide it with 2. So what was the pK1 value? We calculated over here 2.34 and 9.6, right? So 2.34 and 9.6. Divided by 2, that will give us how much? 12 something divided by 2 will have almost like, I think, 5.97 value. So the isoelectric point of glycine is 5.97, right? 5.97 approximately, we can say it's approximately like 6. So I hope you able to understand today's lecture. Today we studied about let's go back to what we studied. We studied about the zwitterion. So zwitterion is actually a molecule that has both positive and negative charge. And then I showed you how does a zwitterion look like. We also studied about the concept of acids and bases in terms of protonation. So when a proton is donated, that will be an acid, and when a proton is accepted, that will be a base, right? And then we also had I also showed you that when in low pH, the hydrogen ions are more in number, therefore the NH2 will gain a positive hydrogen atom, leading to a positive +1, and then this one has no net charge. This is a zwitterion, and this one, because of the high pH, this NH2 will also lose its hydrogen atom, contributing its charge, that is -1. And then we have the term called amphoteric or zwitterion, and then we studied about the pK1 and then pK2, which is the acid dissociation constant. pK1 is the COH and NH3 is the pK2. Now we also discussed about the isoelectric point. It was the particular pH at which the molecule or the amino acid loses its charge. Like, you know, there is no electric charge at all. There is net 0 charge. And then we calculated the isoelectric point of glycine, where I showed you that 2.34 is actually the charge where the COOH loses its hydrogen, and then 9.6 pK2 value was the where NH3 loses 1 hydrogen and becomes NH2, right? And this is the zwitterion, right? And then over here we don't have any charge, we don't have any, like, you know, donating or accepting thing. It has just like gained a positive charge over here because the hydrogen ions or the hydrogen atoms are very much like high in number. And then we just calculate it with the formula, that is pK1 plus pK2 divided by 2. That will give approximately 6. So that is the isoelectric point of glycine. So in our next video, we'll try to learn about more isoelectric points of different amino acids. So please stay tuned for that particular